So as I said, what I would really like to hear, after yesterday's discussion, some people came and say, well, we always had these panel discussions on NICE meetings, and it's always the same kind of conclusion that, well, we don't really know enough about neuroscience and shouldn't really do this. Maybe we should really focus more on neuroscience, not start building devices and computers. And so there seems to be little progress. That is the general opinion. And I think that's not true. In fact, we have now the 4th conference in a row, and to me, my impression is that the progress is quite substantial, in particular also in the system construction and operation. But of course, I would like to hear the opinion of the panelists on where they think the progress is, and then maybe at the same time also where they see that next year at this meeting we should have reports and presentations. So should we start over there with IBM? You didn't listen.
I might have the exact statement of the question, so maybe it's better to start.
Then we start with Johannes.
Okay, obviously I support building hardware. And I think it's necessary, because if you look at biology, you see that it's tremendously complex, and we won't be able to replicate its power with digital CMOS technology. So we have to find a new technology which allows us to implement the essentials of biological information processing. The problem is we still do not know what they are, and we do not have the devices. So you can say, okay, we do nothing, but I think we should take what we have. That means we take the limited knowledge we have, and we take CMOS and the limited number of memoristic devices we already have, and try to do the best to be prepared and to be able to take all the proceedings of the biological research and the device research into the next generations of our systems. Because if we wait for, let's say, computational neurobiology to give us a blueprint, we will wait forever, I think.
I'm definitely a hardware circuits guy as well, so I'm all about building interesting hardware. I do come from a slightly different perspective. I guess I'm more interested in just thinking about, I guess, in theory, okay? And I don't know what the killer application is. I don't know if there is a killer application. But in theory, I'd like to think in terms of, well, what are the applications and how can we design good computing systems to solve a problem? And there's a lot, what little we do know, there's a lot that we can draw from biology and build interesting systems, even though we don't have a complete representation of a neural system. And I think some of the examples, we talked about the Google DeepMind playing the game. Where I'm from, in Tennessee Valley, with Oak Ridge National Laboratory being right there, we talk a lot about big data problems and the role that machine learning plays in these. So I think that we're at an interesting time where, even though I have a hard time, as a lowly circuit designer, figuring out what these applications are, certainly what is the killer application, I think we are at an interesting time where there are applications that necessitate machine learning. And I think that machine learning and other like applications do necessitate some neuromorphic or neuro-inspired architectures. So certainly this is certainly worthwhile, and I'm very pleased with the progress being made in this community.
So I think the biology is very important. I think many of us here will definitely agree that this conference is about the interface between neurobiology and computing. And after all, the brain is still the gold standard of computing. Whether you argue whether the brain actually computes or not is a different matter, but at least in terms of feats of intelligence, we can definitely argue that human intelligence is there, even though there was a little blow of human intelligence just last night, but I think it's definitely there. So there's definitely a reason for moving forward with taking biological inspiration in building machines and electronic chips that are inspired by it. Right? So definitely the level of detail is still an open question. We don't really know, and then until we really know how the brain works, we can't really throw away too much detail, right? Once we know, perhaps then we can start abstracting, but until we know it, it's hard to abstract, right? So there are two main, and this is also great. So once we have a machine that is biologically inspired, right, there are two application domains. One is then engineering, right, just applying those chips and systems for hard problems in machine vision, machine learning, right? And I guess it's obvious that there's definitely good application. The other application would be for computational neuroscience as an accelerator. And there, I think the litmus test will be whether not just us as enthusiastic neuromorphic engineers, but also whether computational neuroscientists will actually really use those tools. And perhaps things are starting already, but so we haven't seen too many enthusiastic people at the Cosine workshop saying, oh, I love really this new hardware, and I want to really use it. Right? Because much of computational neuroscience has been focused on problems at the scale of perhaps a few hundred neurons, and very little work has been done really at problems involving millions and perhaps billions of neurons. And even though there things may get interesting, there may be a phase transition, we don't really know. And it'll be important for computational neuroscientists really also to be engaged in this and take advantage of all the hard work we're doing. But we'll see what happens.
So I think I might take a slightly different perspective on the question, in the sense that I think the biological inspiration from the brain is such that it's a system that is really well co-designed between the algorithm and the hardware. You have this great matching, and I don't know, but maybe that was evolution that helped those two grow up together. And I think looking at it through the context of how do the algorithms match the hardware that we have, and how does the hardware inspire the algorithms that we look at? I think that is really important because our current applications are really well matched to certain types of hardware, and that dictates the applications which do well. And so I think it's really important to think at it through the lens of what are the algorithms that are really important. What algorithms can we show actually do something different than our current algorithms, but are not well matched to our hardware? And what hardware would be well matched to those algorithms? And I think for the biological inspiration side of things, there's this prior that we have, this hypothesis that hardware of the specifics of the biological spiking and all these types of things, that is tied to some algorithm that is really fundamentally different and useful. But I think we're missing a key demonstration to shoot for about what application would really be beneficial that could use this type of matching with that type of hardware. So I think everyone's sort of going at the thing they're all sort of going towards the same place. But I think it's really important to have both algorithms and hardware together in mind when making advances.
So I take a very practical kind of viewpoint on this, in the sense that I think from a biology point of view, we certainly don't understand completely how the brain works. In fact, we probably only understand a fraction of how it works, but nonetheless, there's been a tremendous progress in doing this. And so we have a lot of knowledge and inspiration at our disposal. And then on the other hand, from a technology point of view, even though the challenges seem, very, very large, we still have a lot of tools at our disposal. And I think if you look at both of these, we can make a tremendous amount of progress. And as far as sort of the killer apps are concerned, I think this is a very good question, but I liked the perspective that was given the other day that, language is an it's a universal thing. It's a very human thing. It follows rules to some extent, but there's really a large element of fuzziness with it. So I think of this as being an amazing app. And then I look at the kind of task that involves sort of language and perception that a child could do. For example, go to a movie, watch the movie, and come out and tell you in 3 sentences what went on in the movie. And this is a very human task. So these are the kinds of applications that I think would be killer apps to get a machine to do, and obviously they will require a lot of innovation at the hardware level, at the algorithmic level. But I think these are the challenges and the directions.
Okay, thank you. So after this first round on the panel, can we get interventions from the audience? And I see Steve moving. Very good. And Winfried, excellent.
So everybody here is kind of building systems. And what I think is interesting is what we use them for. Now, something has changed since last year in Albuquerque. And what has changed is that over this year and coming months, we have 3 very large-scale platforms available for people to use. Okay, True North is now available, very significant system. The Heidelberg system and Spinnaker come online this month. Anybody can get to them. And so my question, with Spinnaker, you can model 100 million neurons, 100 billion synapses. What are you going to do with it, right? I think this is a very big question. Now, my observation is that the news from last night about AlphaGo has created a huge amount of excitement. What's going on there? Well, DeepMind is 2 men and a dog in London who built a program to play Atari games. Right? Now, this is not a serious application, right? But it's produced serious results. And that's led on to this thing that's winning Go. Again, who cares if computers can play Go? It's not an important application, but it's a very important message about progress. What are we going to do with neuromorphic hardware that will stand up against what DeepMind did last night? That's the question. We have the platforms. What we now need are the challenges, the things to use those platforms for that will put us in the news the way DeepMind is now. How are we going to do that?
I must say I don't see our work in competition to this digital convolution and deep networks. Yeah. I'm very sure that only spikes lead to some progress in understanding biology, and without spikes is totally uninteresting for me. So I think we have time. Continuous time is also very important. For me, I have a totally different goal. What I want to have a system which runs continuously all the time, like a living being does, not being switched on and off and doing single-step experiments running for a short time. That's my goal.
I would like to add that I think this was a spectacular achievement, but it's a very specialized achievement. And I think what we want to think about is a much more general goal, something that doesn't do one thing, but that can do many different things and take inputs from many different sources and still figure out what's important, what's relevant, and take the right action. So I think there's still a big step.
But what is it? Specify it.
Well, I mean, I think I was trying to give it some examples before. I'm not trying to be so specific in giving a benchmark, but I think really understanding language is one thing. But we take language in inputs from many different ways. You speak, I hear, I read, and I'm able to integrate all of those and decide what's the relevant one, and then go on. And I think this is a very daunting task to try to get a machine to do, but it's maybe not something that it is something that we should ultimately aim if we want to make an intelligent machine.
So one feedback I will have about the AlphaGo result is that what's interesting is they identified a problem, and the problem was really that of discrete optimization, right? Was of these situations where you have these discrete steps you're taking, and they identified a problem domain where they could get clear feedback about whether or not they were doing good. That you have games are wonderful in that they both generate data for you, and they're also clear about whether or not you win and you lose, and so it is really, I think there's a lot of value to going outside of ImageNet and going outside of offline benchmarks, but there's also a lot of value to having a standard for what your online benchmarks are, so that you can focus the community into targeting some of these things.
I totally agree, and so it's an interesting problem. Computer Go, if you think of it, has all elements of what we care about in behavior. Right? There is definitely perception. In fact, the type of perception is very visual. The board is really, the patterns on the board are really visual patterns. There is motor planning, there's execution, there is definitely learning, there's reinforcement learning happening, reward-based learning. So it's definitely a good is actually a good benchmark for neuromorphic, I would say for neuromorphic engineering as well. And interestingly, the approach taken by DeepMind is not too far away, I would argue, from neuromorphic engineering. If you look at the approach taken, it's reinforcement learning, right? Or temporal difference or other approaches, right? There's less of Monte Carlo. There is more of right. There's always a combination of search and all that, but you can definitely argue there's a lot of neuromorphic elements, or at least neural-inspired elements in that too. So it'll be very interesting to see the network that has been trained, if it can be shared, and see if it can be mapped onto a neuromorphic platform, and perhaps even have a neuromorphic platform go through the same exercise of using the same data sets, training, right? So learning to get at the level of a human. So I think I totally agree, Steve, that this is a great benchmark, and we should definitely look at it.
So I'm Winfried Wilger, IBM. Let me start out with a provocative statement. I have a feeling that we already know too much neuroscience for the goals of building interesting machines here. I mean, neuroscience conferences have, 30,000 attendees. How many more details do we know? I think the much more important challenge is to extract out of existing knowledge algorithms to do something useful. And let me define what I personally think is the interesting thing. On one hand, we have deep learning on mostly static, supervised label data sets. That is a steam rolling and doing very well. No need to change that. But on the other direction, I think, should be truly intelligent machines. And let me define what I mean by that. These are machines which are continuously learning on their own, unsupervised, detect patterns, predict patterns, and act on this. Okay? This would be the definition of an intelligent machine. And it should have goals which, through, say, reinforcement learning, are superimposed by the maker of a machine, by us. Okay? A little bit like hell. But as a practical kind of benchmark, I think building robots based on that would be a very good test, because a robot is a microcosm of an intelligent machine. It needs to get sensory data, make predictions. If I do that, will I fall over as in a walking robot? And it needs to do actuation. So I think that would be a big goal, which the second branch of the field should be following. Building intelligent machines in form of robots.
I totally agree.
The cognitive age, embodied cognition, yeah.
I think closing the sense-action loop with a spike-based local learning controller is what should be one of the next goals. Mm-hmm. And let Google do the deep learning stuff. They can do it better.
I will say, within the deep learning community, I think there's a lot of value to video games as a proxy for robotics, not because they're very realistic for real life, but because they tackle many of the same issues, and then you don't have to sink 4 or 5 graduate students into learning how to do robotics. So you have infinite data, they can run faster than real time, and evoke many of the physical learning that you need to do.
Nice demos.
Yeah, and everyone loves video games, so it's a nice demo.
Then I have 2 provocative statements or questions for that. Because one, if you do the simulations, you risk of spending a lot of time on getting the simulations to work. But when you actually get to this real-world cognitive agents, you find that all of the things the tricks that you use that were working in the simulations will not work, likely, and you have to redo everything from scratch. So you might as well do it directly on the hardware physical system. And once you have the hardware physical system, why do we need to have these exascale computing platforms if we just want to reproduce, for example, a bee or a fly to begin with, something that we can actually start to tackle? That's the 2 questions. Why should we do it software, and why do we need to do large scale?
Shall I answer first, or you? Okay. I think one problem with robotics is that reality is too slow. If you look how long it takes nature, as real organisms, to learn, we will never finish if we stay with real-time systems. So what we have to do is a two-tiered approach. We need accelerated, simulated, simplified systems for getting the basic structure right, and then refining this in real environments. I cannot promise that it will work. I mean, that is just what I think it should be.
I sort of think of video games as a necessary but not sufficient situation that, the types, depending on the games that have been mastered so far are not very complex, and don't involve long-range planning and a lot of these types of issues. And overcoming, you'll necessarily have to overcome those challenges in many situations for real robots that want to do similar types of things in real life. So it's a stepping stone that by no means is the full stepping stone, but seeing that so much of the world also is digital these days as well, the lessons that you can take there and apply to domains outside of video games are also very interesting.
Another advantage of video games, or games in general, such as the game of Go, is you can quantify complexity in very clear fashion. And you can also actually control complexity. You can vary complexity. For instance, in Go, you can change the board size or so, right? And so you can observe then, say, performance versus, or scaling of performance with size of a network or complexity, right? So they're nice tools. And of course, eventually, you definitely want to go in the real world. And clearly, Carver Mead really advocated that. So the whole field of neuromorphic engineering really started as a hands-on thing, and this will definitely keep going.
Todd?
So, well, as far as potential sort of challenge problems go for neuromorphic community and things that would be both, I think, noteworthy and valuable, I've thought for some time that one might be essentially training a system to drive a car using predominantly visual inputs. And I chose that one in part because it's going to be very computationally intensive. It's very biologically relevant. It's very noteworthy if we can do it. You can set it up initially in a virtual world, probably with a game, so that you don't have to actually kill anybody the first few times you do it. But I think it would be a kind of a great challenge problem if we could somehow get our minds around how to do it. And we wouldn't necessarily have to start with a purely neurobiological approach. Either we could take a more machine learning approach and map it to the neuromorphic hardware early, if that's the right thing to do, if that's the easiest way to get going, and then maybe see if we can feed in more biological features once we start having some success. So anyway, that's just a thought. I thought I'd see if you guys think that's a reasonable thing to try. I mean, how far are we from being able to do such a thing?
I thought Google is already driving cars.
But they're not doing it purely with vision systems that are entirely trained.
Right, and a lot of those are like LiDAR systems, which will fail in the rain. So vision systems are really important for heavy fog and rain type conditions and those types of things.
And I want to teach the system to do it, right? It's got to learn what the world is, and it's got to learn how to respond within it without us writing too many rules for it and without making too many mistakes. So that's the thought.
Actually, I think this idea of injecting step-by-step more biology is an interesting one, because that way you can systematically find out whether those things you see in biology are useful or not. So that is,
yeah, like you could just wipe out a whole layer that's, currently a perceptron layer and stick in a biological layer. I don't know, maybe that's a crazy idea, but
I personally don't think that it's possible at all. I think the spike-based coding is so interweaved in the system that you cannot take one part out and exchange it against anything else.
Probably so.
I don't know, but that's what I think.
Well, Wolfgang Maas will tell us neurosampling is a means for taking a machine learning approach and transferring it into a spike-based representation.
Yeah, maybe on this level you can imagine it, but the system, I think, has to be somehow homogeneous.
So maybe to follow up on Todd's comment in terms of having a system that learns by itself, I think one thing I'd suggest as a challenge is build a system that can do it without a single algorithm. That's what biological systems do. There is something going on there. We're able to describe it as an algorithm, turn it into a machine learning system. But the challenge, again, I don't know if this is realizable or not, but have a system that can do it natively, implement it internally, but we don't have to write the algorithm in the first place.
So I kind of agree that that's a great long-term objective. I was just trying to give us something that would, sort of focus us and be meaningful if we, and sellable basically if we had some success. So I agree with you, but in the short term, I don't think we're there yet.
I'd also just take maybe a minor exception with that, which is just that those types of systems, I mean, since you have this giant meshing of the algorithm and the hardware, if you can make hardware that does it without an algorithm, the hardware is the algorithm. So, I mean, that's obviously, a good level of implementation, but you're still constrained by the same inductive bias that you would have put into the system.
Definitely so, but I'd add to that, I mean, one of the key things about neural systems is there is no software, there is no hardware. It's the system itself is doing both functions just the way it is.
So I wanted to comment on Todd's suggestion. I have a reasonably high quality German car, which it's not fully driverless, but it has a vision-based driver assist system. And it doesn't like bad weather, which means in the UK it's useless most of the time. No, I mean, it has an active cruise control which uses vision to detect other vehicles, and in heavy rain it just gives up. So even though it's vision-based, not LiDAR-based, the vision can't cope with the conditions. Well, it hands control back to me, so it assumes I'm better at this than it is.
So you see, this is intelligent. It already is intelligent.
So this is Miao Hu from Headpar Labs. So I have a naive question here. So I'm just really curious that imagine your brain cells or neurons can use communication methods other than spikes. What will happen? So I try to understand, is that the spike communication is really the advantage, or is it just the limitation of our biology system? So, I mean, if in your simulation or your hardware, you change the parameters and force your circuit to use other methods other than spikes, can you prove that they will always perform much worse than spikes? And and also for the contribution of spike communication, so how can we decouple its contribution of performance other than like event-driven activity and local memory? So thank you.
So shall I answer? Or I think it's not the spike communication which is important, but that the spike carries the temporal information. And you have seen it this morning in the talk about the grid cell coding. You can do, if you have a continuous time system and get rid of the idea of frame-based or single event stuff, then time is the most valuable resource you have. You can link together objects. You can do binding by using phase. And all the learning correlation in time can be measured. So I think this is the reason why spikes are ubiquitous in the biological nervous system. Yeah.
I think it's important to point out that biological systems have both analog and spike-based computation systems. So for example, in the retina, all the computations are analog. And an insect neuropill, and all these stuff that's going on in bee brains and jumping spiders and so forth, the communication is mostly in the form of dendritic communication. So that's where the computation is happening. You have the cell bodies that live on the outside of this nucleus. Yeah. The dendrites all just sort of innervate in there. And it's just dendrites talking to dendrites. It's not like your conventional sort of input-output model where the inputs come on the dendrites and then the spikes come out the axon kind of thing. It's just a big hairy mess, and then it's all analog computation in there. And so I think, one lesson I think you can draw from that is nature does both. And so where it uses spikes, it's probably for a reason, right? It's sort of evolution sort of chose to do that as a spiking system because it's not like a constraint of biology that it has to do spiking. There are clear examples where it's analog and clear examples where it's spike-based. And I think there are probably important lessons to be learned from that.
I think it's great if we can understand the richness of information that spikes are able to transmit, but we also have to face the reality that we don't have the same system. We don't have the same low voltages. We don't have the same neurons. And so even though that may be the most efficient, or maybe not the most efficient, but a very efficient way to transmit information with that system, it may not be true for our system. But just to understand how neurons communicate, of course, it's incredibly useful. But it doesn't mean that we have to do exactly the same thing when we don't have the same tools.
Although if you look at the way we communicate over the internet, this is asynchronous communication, and there are packets being sent, right? Not quite like spikes, but at least they're packets. And so there may be a reason why the internet evolved that way, and brains also do this type of event-based communication.
Well, I mean, again, I think it depends on what is the information you want to transmit. I mean, if it's an intensity, I could transmit that as a single variable. If it's a rate, I could also transmit that as a single variable. But if there's some other rich information that could be more efficiently transmitted by a series of spikes from one neuron, and then another series of spikes which conveys a different piece of information or a corresponding piece of information, and convolve these two really give you an efficient way to transmit a lot of information, then it's useful. But it really depends, I think.
I just wanted to point out that there is a paper by Kwabena Boain that shows that the optimal transmission method that minimizes power and maximizes bandwidth is pulse frequency modulation using spikes. So it is an optimal method of transmitting information.
So a book that's been referred to before is the Sterling and Laughlin book, and it argues, I think, quite coherently that spikes really emerge in biology when the communication distance is above a certain critical minimum. And that for very short-range communication, such as in insect brains, you don't need spikes because the information gets there without spiking. But for larger nervous systems, the communication is too noise-prone, too unreliable in analog form. So the argument may be that spikes emerged to establish reliable communication over a distance greater than about 1 millimeter, I think. However, once spikes emerged, I think nature has then found ways to use those, right? So I think they're functionally, they're not just covering for the deficiencies of analog communication. Evolution has changed the way things work to exploit the fact that spikes convey information in a particular way. And I think one of the big demonstrations of where spikes do much better than standard computation is in the event-based vision sensors. Okay, that's a clear example of where you get far more information, far more efficiently using spikes than you do with conventional numerically based stuff. And I think it's probably the point that Giacomo is referring to, is that if you want to send a single value, then sending a number is fine. But if you want to send a continuously changing variable, then how many values do you have to send, how often? And you could do it much more efficiently by sending sort of up-down events as the DVS sensors do. So I think you can make a case for spikes even in engineered systems that we already understand. Okay, it's not universal, but at least there's one existence proof.
And also, the analog communication in insect brains, for example, or what also is in vertebrate brains, there are gap junctions. I think this was not the discussion, or it was more the contrast between using convolutional networks or using just numbers at a fixed no time at all. Just saying now we process this set of data and then we have a result in contrast to spikes. It was not about the contrast between spikes and the fully analog communication because this is out of reach, I think, of most of our ideas to do this in the complexity this in nature. I mean, you need numerical compute power to simulate this. It means it's all coupled differential equations. If you really want to simulate this, I think it's impossible at the moment.
So there are two aspects of a spike, right? So one is the sparseness in time, and clearly besides the fact that the sparseness helps in communication, it also helps in temporal coding, right? In which this time can be really used for, right? Whether it's in imaging or in optical coding, or whether it's in Cortex. There's another aspect of the spike, and that's the discrete amplitude, 0 or 1, right? And so the discussion we had earlier today, when Bill Daly was presenting this architecture, which is convolutional based, in which there was a great advance in the efficiency by detecting non-zero elements and then only doing the work when actually there's a non-zero activity, right? So the discussion there was based on, yes, so there's definitely also event coding that can be used advantageously in convolutional networks and other deep learning architectures, right? But there the amplitude was multi-valued, right? It had some analog depth. So the question whether analog or multi-level coding is important can also be debated on the fact that if you look at neural architectures, most neural architectures use sigmoidal type units. Perhaps now with convolutional nets, it's slightly different. There are also some other rectifier units, but at least in the old days of ANNs, neurons were mostly those actually even just hard threshold units, 0, 1, sometimes sigmoidal. And so then there's only 2 levels anyway. So in a sparse representation with those units, you might as well think of those as spikes and transmit them accordingly. So maybe it's just a philosophical point, but
yeah, I just wanted to build off of that and maybe just throw out a crazy idea, which is, so I was talking about the importance of matching to an algorithm that doesn't lay well onto hardware right now. And I think what the deep learning community is seeing, both through a lot of work looking at how over-redundant neural networks are, not just convolutional, but recurrent, that you only need 10% or less of the network to actually do the computation. So sparsity is it's so present within neural networks, even if there hasn't done the proper regularization to expose it. But there's the computation is fundamentally sparse that's going on inside of these networks. A second stream is in temporal processing, things like LSTM, long short-term memory networks. In essence, if you tune the parameters correctly, I mean, you can get a whole bunch of interesting dynamics with those, similar to a spike or something like that. And so what GPUs don't do very well right now is handling data-dependent sparsity. Really knowing unstructured sparsity that, of activations where you don't know exactly where the sparsity is going to happen and all that type of stuff. So if you had an accelerator to be able to do a sparse matrix multiplication that was constantly changing with the data, I mean, there's something that we don't know how to do very well, but clearly is inherent in these algorithms. Even when we try to make them dense, it turns out they're actually sparse. Crazy idea.
Any other interventions from the audience or from the panel? Then I guess we can probably close this final panel discussion. And there are a few things that remain to be done. And the first is that I wish to thank all of those who contributed to this workshop. That is in particular, of course, the audience that attended, although we have been declining a little bit. But we came a long way from the first meeting 4 years ago. We saw the statistics. It was 50 in the first meeting, and it was almost 200 here in Berkeley. And that's quite impressive. So it means that there is interest in this field, rising interest. And I think it's clear that we will continue doing this workshop. We have to decide on the final location. It may likely to be here in Berkeley again, but it's clear that there is a is a need for this kind of workshop with its discussions and contributions. And so it's great that you contributed. I thank all the speakers that really made exciting contributions, and in particular also then the follow-up panels, which were all very interesting. We just saw that there are really interesting contributions which you carry home somehow and keep thinking about these things, which will then hopefully influence your work. And I wish to thank Murat, who has been running this organization now for a while and made sure that this workshop really happened, and I will leave the last word to him, of course.
So likewise, I'd like to thank all the attendees, all the speakers, and people that have contributed to the event. I also wanted to thank Bruno specifically. He has been our host, and Natalie Terranova, who has helped greatly with the organization for the event, and Georgianne Sack behind the scenes. Again, our plan is to reorganize shortly after this, or regroup shortly after this event, and plan for next year's. So please send us your comments if you would like to get involved in the organization and also in the content for the next year. We look forward to your involvement in your suggestions. With that, thanks again, and we look forward to seeing you again next year.